Dear students, welcome to the organ printing course. So in this lecture, we'll discuss about the printability. Basically, we'll define printability for extrusion-based bioprinting systems and what are the different parameters that dictates or decides the printability for an extrusion-based bioprinting setup. We'll discuss all these things here. Let us first start with understanding printability. What is printability? In for extrusion-based bioprinting system, printability basically defines as how well a printed construct adheres to the dimensions of its design. That means when we make up the CAD model, then and we then we, even then we when we print that structure with that CAD model, then whether the printed structure can be of same dimension, same resolution to that CAD diagram. We actually determine the printability by that. That means, suppose many a times in the literature you can find that when they define printability, that the buying, suppose they develop a novel buying, and then they decide that whether the what is the printability of that buying, then they choose technique where they print lattice structure. Lattice structure means they print lattice structure where first layer, suppose the first layer, the lines are suppose designed in such a manner that that they are facing towards a particular angle. Then the next layer, the lines will be 90 degree to the preceding line. So now here in this case, basically you can print squares, right? Basically squares of that structure. Now when somebody print a 1 by 1 centimeter square and then evaluate the area of the printed construct in relation to the CAD model, then then there itself they can actually understand or they can evaluate whether that square, now what is the size of that square in case of printed subtract or printed subtract, and in case of CAD model. Now if you compare these two, you can very well understand what is the dimension of this. The another thing is the whether the square is perfect, circular, or any deform is there any deformation. Those things also we can understand. Now then this also, when we suppose if we print a line through the extrusion based bioprinting, right? That line, whether the line is straight, the printed the fiber is straight or not, that can be decided by the whether the uniformity of the printed fibers can be quantified by the straightness of their edges. That means when the printed line, we image that printed line first, and then if we can divide that lines into pixels, or then we can count the fibers. When the fiber is there, the fiber is actually how many pixels the fiber is actually occupying along the length, right? Whether the same number of pixels is occupying along the length, if it is so, then the fiber is straight. Otherwise, if there is a wavy, the fiber is wavy, or there is some part, if the dimension is less, suppose the width is less or more, that can be defined as the material is not very good in printable, means that bioink is not printable in that kind of with that kind of extrusion based bioprinter under the optimized process parameters. So those things actually, that's why that this is how, like, the printability can be evaluated for a two-dimensional object printed with the bioprinter. Now the same thing, if we want to replicate the same thing for three-dimensional, then what will happen? Then the same kind of square will be again printed, but in this case at least three layers will be printed. So that the first layer, suppose first layer is printed in this direction, the next layer will be at 90 degree to that first layer, again the third layer will be 90 degree to the preceding, the second layer, and like this the whole three layer will be printed. Now in this case again, this few of the parameters will be again evaluated, like whether the line is straight Thus, whether the line has this straightness or not, whether the line is deformed or not, what is suppose the thickness of the line, whether the line is resolution is same or not. Suppose I want to print a 400 micron line, but I end up getting a structure of 600 or 700 microns. So that's a deviation from my actually original design. So what is the deviation that can define the printability? Suppose if the deviation is not much, suppose we have a tolerance of 10%. So that can be taken into consideration. Suppose if I want to print a 400, I have a tolerance of for 10%, then I can up to 440 or 360 to 440. If I want to print a line with in between these two dimensions, in between these two margin, upper margin and lower margin, then I can, that is acceptable. That can be acceptable design. That can be acceptable printed structure. So like this, researcher in literature generally they evaluate the printability of the bioink using any of these methods. Now here the for 3D again the extent of merging that occurs between stacked layers. Like suppose when we actually print the lines, one line on top of that another line, many a times these layers, stacked layers can merge. That means I cannot basically after printing I cannot actually find out why what are the different things or whether three different layers, distinct layers are there or not. Most of the time these layers will be merged with each other and then I will not be able to delineate the lines, delineate the different layers. So that by this way also you can actually, and then what will happen in that case also the widening of the layer lines will happen. So that would happen. That can be easily be seen for certain bioinks. Whether the both the area ports compared to the theoretical extent. Again the area of the pores. Suppose if I created a lattice structure, a square, then the pores, whether the pores are perfect rectangle or there is a circular or there is a deformation. So by this actually we can understand. We also if the pores are perfect, if the pores are perfect square, that can have a implication uh, that the structure is the bioink is very good printability or the system is have a very good printability within the circulating pores. If the pores are becoming circular, that means there is a widening or deformation of the spreading of the lines that can lead to circularity of pore. Otherwise, actually, as per the design, suppose as per the design that is a rectangle design, I end up having a circular pore. So that is not actually useful, or that is not acceptable for the bioprinting, because that bioink cannot provide you a good printability. That means you cannot make up a good or you cannot print a very good structure, and that cannot make it print a very good structure, or the print fidelity would not be that great. As we have discussed in our earlier lectures, that printing fidelity generally defines now whether your printed structures adheres to the dimension of a design or the design thing. So if they are very different, then the printing fidelity is not that great. So circularity if the pores are becoming circular, that is also not good sign. So that again that tells us that the print bioink is not printable with the set of conditions where you are trying to print them. Other than this, few of the literature they also evaluate whether the where suppose when you are extruding the bio extruding the when you are extrude suppose when you are extruding the bioink through the extrusion nozzle at certain pressure, whether there is a drop formation of that bioink or there is a fiber formation or there is the widening of the fiber happening in the when it comes out of the nozzle. So that things like suppose there is a drop formation, that means it is under extrusion. That means that pressure is not optimum for extruding the material through that nozzle. Now you need to increase the pressure. Again, if you increase the pressure further, then if there is a fiber formation, that is perfect. If suppose if the fiber is formed but the material is getting wider, the fiber is getting wider, that means it is over extruding the material. There also again you need to optimize your pressure to get into a perfect fiber formation. So fiber formation is again an indication of printability of the material at that set of conditions. Another way to evaluate printability is when you are trying to print a line over bridges of increasing distance. Suppose I put at one line several bridges, like one first the bridges are very close to each other, then the next bridge is a little increasing high, increasing the distance. With increasing distance, if I keep the bridges and then I try to print a line on top of that, what will happen if the ink can self sustain itself over the bridge? Then that ink could be very good. That ink could have very good printability. Suppose with increasing distance, then we can evaluate at what distance the printed line can support itself, and there is no sagging of the line. Suppose there is two bridges here, and my printed line is suppose here, and it is perfectly fitting on those two lines. There is no sagging, then it is perfectly printable. That's very good. But if there is let's suppose the through printed line, if there is a sagging like this, then that ink cannot hold itself, and there is a deformation or sagging of the ink. So that means that ink is cannot able to we cannot able to use that ink for long bridges. So like suppose when the structure has like a long gaps or long pores, so there that ink cannot actually fulfill that requirement. So this is another way to determine the printability. So but this kind of bridge distance test, my this can classify certain bioinks as unprintable, because if most of the time the hydrogel or polymer solutions bioinks, they have this thing like they cannot hold themselves, or they will just sag or deform if there is a gap between the in the preceding layer. If there are bridges and if there is a gap between the more gap between the bridges, they will always sag, and that can classify them as unprintable. In certain bioprinting system we have discussed earlier, one such thing is 3D printing in support bath. There there the they use support bath or ink as a support material to hold the bio ink during printing. So we have seen this because support bath material, they are like Bingham plastic, where they are like solid unless you put a pressure on that. But when you are dipping in nozzle and then printing the structure, plotting the material within that structure, within that support bath, that time the support bath actually holding the material, because they are like, because when the pressure force gone, they again become a like solid. So they are providing support to the printed structure, but using that support bath can again improve the printability of your bioink, because in this case the bioink is cannot bioink is because the bioink having the support, so they are not no longer getting deformed, getting sagged, or getting widened, right? Because here the support that can actually help to classify several bioinks those are not printable or unprintable during, in case of other conventional bioprinting, where you need the ink bioink to have hold themselves, or the shape should be retained, they should not sag, they should not be all these things. So these all things can be eliminated by the use of support bath material. So the use of support bath eliminates any self-supporting limitations of deposited filaments. That means here the support bath can provide the support to can provide support or hold can hold the printed line or structure during the deposition, and it facilitates self-retention. Print fidelity would be very good in this case. This also bioink other that otherwise can classify as non-print unprintable in the normal in the without support bath, suppose in the conventional bioprinting, but can be classified as printable in a support bath. So that means we can now define the printability doesn't describe any one material. That means we cannot classify the bioink based on certain taste that the bioink is not printable, but it also depends on the whole lot of system, like the bioprinting system as a whole, including the ink materials, additional support material, the printing condition, and the printing modality. So all these things together can describe a material printable or non-printable. Because we have clearly seen the earlier example, that a bioink can be very well printable in a supporting bath, but cannot be printable or unprintable in a conventional bioprinting, where we are trying to print them on a petri plate or a glass slide. So this is how, so printable, when we are talking about printability, it is we need to consider the all the things together, like the bioink, bioprinting systems, support bath material, printing conditions, all these things when we, and then the modality, all the, when we consider all these things together, then only we can classify, we can actually classify some materials as printable or non-material. So this is how the printability of a material can be decided. Now we have seen some ways how, suppose how to address the printability concern for extrusion based bioprinting, right? Because in earlier classes also we have discussed that the printability of a material, printability for extrusion based bioprinting defines the challenges that the printability of the material can be improved by increasing viscosity, or in turn by increasing the concentration of the material, molecular weight of the material, and also the networking properties of the material, right? All these things we have discussed in our earlier classes, earlier lectures about all these things. So, but for cell culture, the requirement is, say, for cell culture, the cell thrives in a low viscous, in a open porous network or low viscous environment. But for bioprinting, so there is the two opposing requirements here. For bioprinting, extrusion based bioprinting, the material requirement is it should be high viscous, high stiff material, stiffer material is required. But for cell viability, less stiffer, less viscous material is required. So these two opposing challenges are there, and we have to address this issue so that we can come up with a strategy without actually increasing the viscosity of the material if we can improve the printability. So that is why in this, like here we'll discuss what are the different ways by which we can actually, by only the material, using the material based strategies to improve the printability of an extrusion based bioprinting. If you see materials with lower viscosity, means this is actually ideal. Materials with lower viscosity but can rapidly recover their viscosity following deposition onto a print surface, either through shear straining behavior or through a rapid and often in situ salt to gel transition. Because in extrusion based bioprinting, we have earlier we have discussed that when the material is actually extruding through the bioink, when the material is extruding through the bioink and it is getting deposited, in that process the material is fluid. Its material is fluid as in, suppose in salt state, but as soon as it come out of the nozzle, then trans it should sorry it should get gel immediately. So that transition of some salt gel to gel state, that should be very fast, and as soon as it come instantaneous. By this way, we can improve the printability of certain low viscous material. Right? Either you can this thing. Shear thinning behavior is another thing we have discussed, where the suppose the material when it is coming out of the nozzle, that time it is under high shear rate. So that high shear rate, because of the high shear rate, the viscosity comes down. So it facilitates the extrusion of the material through the nozzle. But as soon as the material comes out of the nozzle, there is no shear force. The force is not there. That time the material viscosity again goes up. But if we using a high shear material with very high shear behavior, then that helps us because the viscosity that when it is coming out of the nozzle, that time that the viscosity is low, that helps to extrude the material at low extrusion pressure. But whenever the material comes out of the nozzle, after that, the viscosity again goes high. That will hold the material, the shape together. It will prevent deformation. It will prevent spreading of the materials, or it will facilitates self retention. So that kind of these two strategies are mostly used for enhancing the printability with extrusion based bioprinting. And most of the polymers for extrusion-based bioprinting are of this category. They are shear thinning nature. The shear thinning nature because this material, what happens, as we have discussed earlier also, the materials, they these polymers as mostly they are having long chains. So these long chains actually get entangled with each other, and there are other kind of interactions, suppose inter or intermolecular interaction between these polymer chains. So that basically forms a network. Network, because of the network, this material behave like a high viscous material. But as soon as we apply shear, that shears actually disentangles the material and aligns the polymer chain throughout the extruding towards the extruding direction. Direction. That means that helps the shear actually helping the materials, the shear force that is helping the material to disentangle and align the polymer chain, so the material can easily be passed through the nozzle due to the applied shear force, and by this way the viscosity comes down. Now there are a number of factors that determines the extent of shear thinning of a material. And as I have already said, for extrusion-based bioprinting, high shear thinning material is very good because that material has initially at low shear or no shear, there is a very high viscous. Again, when you're applying shear or high shear, then the viscosity comes down. So it's this basically is typically the viscosity is high at low shear, it comes down at high shear, and again when we remove the shear force after after extruding, again the viscosity goes high. That means that shear recovery of the material helps in retaining of the structure, shape of the material. So these are the factors like the chain length of a polymer determines the shear thinning property. Because if the suppose the chain lengths are very long, then what will happen? That longer chain polymer of the longer chain will always have a higher chance to get entangled with each other than the shorter chain length. Extent of secondary bonding. Suppose there is some kind of hydrogen bonding, intra or intermolecular hydrogen bonding, hydrophobic interaction, physical interaction, those things are there within the polymer. That also leads to high shear thinning property of that material, because the shear force can disrupt that secondary bonding and the pull and decrease the viscosity of the material, right? Similarly, physical cross-linking is another thing. Suppose that material has some kind of physical interaction between the chains, so that also can help, that also can dictate that also can decide the high shear thinning property of that material. And with the shear force, that kind of force can also be disrupted, and the material can get extruded through the nozzle. Material must also possess high shear rapid shear recovery in order to maintain its printed shape. That means when the material is extruded during extrusion, as we have discussed, during extrusion the material viscosity comes down. That means upon shear the viscosity is low. But as soon as the material comes out of the nozzle, the viscosity again goes high, and the material can retain its shape and then or the printed shape and the resin. So it will again the high viscosity of the material will definitely prevent collapsing of the structure, retain the shape and those and print fidelity would be very good. So enhancing the shear thinning behavior through secondary bonding, especially self-filling bonding, is the way by which you can enhance the printability of an extrusion-based bioprinting. Here means some kind of if we introduce some kind of secondary bonding within the material or again some self-filling bonding within the material. So there are various ways you can find in the literature. There are various ways this is generally done by which the secondary bonding in a material can be improved, increased, by which we can by which the and that can so the printability can be improved. Host guest chemistry is another way to introduce enhance shear thinning property in case of hyaluronic acid inks. That is typically that is being used where suppose there is a host site within the molecule within the polymer, and then suppose there is a hydrophobic pocket. And suppose the molecule mostly the polymer chains in certain regions they are hydrophobic and certain they are hydrophilic depending upon the amino acid sequence. Now there is a hydrophobic pocket where another hydrophobic part of the molecule can get interact and entrap with this thing. By this way, so that will prevent that will have a very high viscosity. But when there is a shear force, that whole hydrophobic interaction can be disrupted and the material can start flowing. Again, when the shear is gone, again this host gas chemistry can help in retaining the shear filling property. Means that means again the high at low shear thing the material viscosity will be high. So this kind of strategy can be very well used to improve the printability of the bio-ink without actually increasing the viscosity very high. Because by if we are doing with this kind of things, then we need not to get bothered about the putting lot of materials or increasing the concentration of the material in the bio-ink so that to improve the viscosity so that the material can be printable or the material can be printed very well printable. So these are the some strategies by which printability can be improved further. The next strategy is the based on the gelation. As we have discussed earlier, that when the material, the requirement for extrusion-based bioprinting is when the material is within the syringe, that time it is liquid fluid, it should come out. As soon as it comes out of the nozzle, it should get solidified. Or that solidification in the earlier last slide, we have seen how shear thinning or the physical interaction can help in to get this retain the shape or arrest the flow of the material to improve the printability. The same thing can also be done with gelation. A rapid instantaneous gelation of the material as soon as it comes out of the nozzle can be done. So triggering rapid gelation of the ink as it is being extruded through the needle so much that that extrusion process is performed on a non-viscous solution. That means if the gelation can be started within the extrusion nozzle itself, but it takes time when the material comes out of the nozzle, the gelation that time the gelation is very fast and it can so that the material solidify immediately. That means the shape it can be retained very fast and the print fidelity would be very good in that case. So that can be done. So triggering rapid gelation, and that is typically this is done when we use ionic gelation or photo cross linking, or other ionic gelation or any physical gelation, temperature induced gelation. All these things can be very well used for in the first case. Photo cross linking is another way to to solidify the material as we have discussed in the earlier lectures. When actually we use a photopolymer, that means that is in the monomer state and monomer at the beginning, but it has also so we use some kind of photo initiator, photo activator, so that when the light is induced, light is on, that time the material can be the photo initiator can get activated and it starts the photopolymerization process. So photopolymerization is another way to improve to solidify the material. Now this many a times the photo cross-linking process is not very fast. It's like it takes few seconds, right? But if that photo cross-linking process can be initiated when the material is inside the nozzle, right? But that can, in that case, the nozzle has to be translucent so that the light can pass through the nozzle and it can actually illuminate the material or strike the material so that the material can get the light energy and the photo cross-linking process starts. So there are some examples in the literature where people have tried this approach by which the material photopolymers, when the printing process actually done, they are extruding through a translucent nozzle. As the nozzle is translucent, the light can pass through it, and the cross-linking process can be initiated when the material is within the nozzle. So this is another way by which the printability can be improved by this thing. Other way is the, if suppose if our material has this thermogelling property, that means the material can behave to two different states below the, suppose below a critical temperature when the material is suppose the material is in solid state or gel state, above a critical temperature when the material is in liquid state. Then what will happen when the material, when we print, when actually we are printing, so basically we can either cool or heat the nozzle. So depending upon our requirement, suppose the material is in gel state at low temperature, then we'll cool the nozzle, we'll cool the extrusion nozzle or the syringe. If the material is suppose in gel state at higher temperature, then we'll hit the nozzle, hit the syringe so that the material is in gel state, right? Or we can actually basically cool during printing. Again, during printing we need the material to be in a fluidic state. Accordingly, we can either cool or heat the syringe and then but soon after they come out that outside environment, if we can able to control that outside environment, suppose the printing stage, if we can control the temperature of the stage so that the material would be able to solidify when it is touching the surface due to this thermal gelation, that can help to, again, that can help to retain the shape of the structure and again retain the, or again in or prevent collapsing of the structure or spreading of the structure, or anyway print fidelity would be very good, right? So printing, and then after that when this is done, again we know that we know that the thermal gelation cannot provide long-term stability. The material can able to, after a certain time, the material can get deformed. By to again to improve the, again to improve the stability of the material, some kind of chemical gelation or covalent cross-linking can be introduced after this physically cross-linking of the thermogel materials. So after post-printing, when the material is actually physically cross-linked, that time we can introduce some kind of chemical cross-linking to improve the shape retention or to improve the long-term stability of the structure. Similarly, we have seen those also in case of 3D bioprinting is support bath. Support gel can also maintain the structure of the printed ink for the till the further stabilization happens. So this is, and that is another way, and we can also introduce some kind of cross-linking when the material is in the support bath. That means the support bath can also induce some cross-linking to the extruded material, so that then after that, when the material extrusion is over, the material printing over, by the time when the support bath gone away, the structure can retain its shape due to the cross-linking that happens during the printing thing. A very good example, suppose we are printing alginate in a gelatin support bath. So the alginate is now, if we mix the calcium ions within the gelatin bath, support bath, then whenever the alginate comes out and getting deposited within the alginate in the gelatin bath, what will happen? The calcium ion will cross-link the alginate, right? And after printing, when the gelatin is suppose the melting away after beyond a certain temperature, when the gelatin can melt and we can get the alginate structure, that time the alginate structure will be always again that get solidified due to the deposition of this due to the deposition, due to the cross-linking of the alginate with the calcium ion. Now there are various other things also to be considered when discussing printability, because in bioprinting cells are the cells are the also the major component of your bioink, because in the bioink there are materials and also we load their cells. So cell number is also cell number, typically cell number can be starting from million to billions cells can be there in the bioink. Now when we load cells in the bioink, then the, the inclusion of these cells within the bioink can also alter the rheological property of the bioink. But many a times, many of the studies, they don't consider this fact that the cell loading can alter the rheological properties or can also alter the printability of the bioink. But we need to consider the cell density, cell number within the bioink also for this thing. And we know that higher initial cell density in the bioprinted construct can help in faster tissue formation if the cell number is very high, because if we want to reach to the tissue level, in the tissue the cellular level is very high. Depending on the tissue, the cells can be, there can be hundreds of millions of cells can be there in a centimeter of size of tissue. So that much, if we want to achieve that much high cell density, then the cell requirement of cells within the bioink is tremendous, right? So that much high cell density, if we can include in our bioink, that can definitely, it can alter the rheological property, and in a way it can alter the printability of the bioink. So presence of cells, that the number of cells can significantly affect the printability of the bioink, because it can alter the rheological properties. It has been found that in some studies they have measured this, when the suppose if we include 1.5 million cells per ml of this bioink, then the viscosity can be reduced up to 2 factors. Suppose by 2 factors. That means the viscosity would be almost half of this, or almost less than half of this thing of the bioink when we add that many cells. Again, if the cell number is increased to 2.5 million per, per ml, then the viscosity can be decreased by a factor of 4. And viscosity can reduce further if we keep on increasing the cell concentration. Suppose if our interest is to increase the cell concentration to 10 million or to 100 million, so you can imagine the viscosity can be reduced by many folds, and that will definitely alter the whole equation of your printability. So then you have to work very hard to print a structure with this kind of with the reduced viscosity of the bioink. Right? And higher cell density can also alter the gelation mechanism, the gelation of hydrogel. Suppose it has been found that at certain cases, if the hydrogel can get solidified with some amount of time, then the presence of cells can again hinder the gelation of that thing. It can retard the gelation process of this of the bioink. So that kind of thing also one need to consider. But and another important thing to consider is this, the mechanical property of the printed construct. If your cell density is very high, that would definitely reduce the modulus of the cell seeded structure. That means the printed structure will not the modulus of the printed structure with same concentration of bioink without cells and with cells, it will be very different. Right? With cells, typically at the initially, the modulus of the initial cell seeded structure would be lower than the actually if we are the print structure is printed without the cells. But higher cell density can always accelerate the hydrogel remodeling. That means the tissue building process can be very fast, because if the cell concentration in your bioink is very high, that because those cells will start remodeling the tissue. That means the cells can again degrade the material, the cells can again put down extracellular matrix, synthesize extracellular matrix, put down the material, maintain a hierarchical order, Actually, the whole tissue remodeling process can be very fast if the cell, if your initial cell density is high. So that's why always it is required for bioprinting, the cell density can be very high. But high cell density can also lead to a larger equilibrium modulus of a tissue after weeks of culture. So that means though at the initially, though initially the cell, the modulus of the cell structure with high cell density can be low, but with time the high density cell can remodel the matrix, and the cell and the modulus of your final tissue structure can be very high because of this remodeling process. And there are numerical models that can actually predict the mechanical properties of a construct with different cell density. That means if you prepare structure with different cell density, and if you can mature, if you mature them, then what will be the effect of this different cell density upon culturing of this thing upon time, suppose weeks of culture, then that can be predicted. And if it can be predicted, that is a very good thing, because that will definitely, you can have a better idea what is the cell number, what number of cell number is required to start your bioprinting work. And there are actually different numerical models have been developed where to predict the mechanical properties of the hydrogels can different cell densities and corresponding cellular mechanics. So there are different types of numerical models are actually developed, where one can easily understand or study the effect of cell concentration on the printability, all the final modulus of the structures, and also what will happen to these things. So these all are very powerful tool to study the cell material interaction, and also the to what is the final outcome of this whole study. So thank you very much for your for attending this lecture. We'll again more see more things in the coming lectures. Thank you very much.